Hi everybody. I wanted to take a minute today to walk through the crystal structure lab that we're doing for our Chem132 class and just sort of orient you to the idea of crystal structures and what kind of math is required as you go through this lab experiment. So I've focused in on the section after the reading in this lab that specifies the cubic unit cells. And what's shown here are the simple cubic on the upper left, the body-centered cubic on the upper right, and the face-centered cubic on the lower left, which are the three most common, or at least in this textbook, the most commonly discussed crystal structures. These are the ones we're going to be focused upon. Sodium chloride on the lower right is an example of a crystal structure that's formed by an ionic compound. And so the big difference between the face-centered cubic on the lower left and the sodium chloride on the lower right is essentially the sodium ions, what happens in between the larger particles. In the face-centered cubic, those spaces in between the larger particles are effectively empty. In sodium chloride, those little spaces are filled with the sodium ions that offset the charge on the chloride ions. So a little bit of terminology here that I want to point out. So D0 here is the unit cell length, or the edge length. And you can see that that's the same across all three of these basic structures that we're talking about, essentially center of one corner atom to the center of the adjacent corner atom. And what I want you to keep in mind is that it is the center of the atom. And so if we were to talk about, blowing up one of those atoms, we're talking about the lines coming out this way. And so when we talk about a simple cubic, and we talk about that material being quite packed together, the one thing I don't like about these diagrams is that they show a lot of free space in between atoms. There really isn't free space. I'd encourage you to look at the online modeling tool that I've posted for you so that you can see just how tightly these are packed. But essentially the simple cubic can be kind of drawn this way, as having these four atoms or these four entities packed as closely together. And that D0 number or measurement is center to center. And so for simple cubic, we have D0 is going to be 2 radius. And that's, one radius here and one radius here. The other 2 radii, or the other half of each of those atoms, is actually in a neighboring crystal cell, unit cell. And so we're not going to count it in terms of this particular unit cell. And that's where we get the numbers that are indicated in the textbook when we talk about how many atoms are located within each cell. For simple cubic, we'll see that that's 1 atom per cell, and that's because it's essentially the 1/8 of an atom that's on the inside of this box in each corner. So there's an 1/8 of, I can't draw it on this top one, I guess I'll do that. It's 1/8 of each of 8 different atoms gives us 1 atom total. When we talk about body-centered cubic, we have the same kind of a setup, in that we have an 1/8 each of the corner atoms. And so that gives us 1/8 times 8 is 1 atom total. And then, oh my goodness, sorry. And then we have also that center atom is another one. So here in simple cubic, we had 1 atom per cell. In a body-centered setup, we have 2 atoms per cell. I'm going to say atoms here, but understand that I mean whatever it is that's making this up. So in the case of the sodium chloride crystal, I'd be talking about sodium and chloride ions instead of atoms. In the face-centered cubic, we're going to have the same corner geometry. So we've got an 1/8 each of 8 different atoms on the corners. So that gives us 1 atom in total. But now we don't have 1 atom located in the center. Instead, we have 1 atom essentially split right in the center of the face of each of the sides of this cube, each face of the cube. So we have 1/2 of each of these atoms on the sides is inside this box. And so we're talking, I don't know how I draw this back and front here, but 1/2 of each of those 6 atoms gives us 3 additional. So we have 1 atom based on those little corner slices, and we have 3 additional atoms worth of material based on the the face located atoms. So when we talk about sodium chloride, we're going to talk about the same kind of a deal in that we're going to say the chlorines, the chloride ions, we're going to have 4 ions per cell because those are the face-centered entities. So we're talking about the chlorines being the circles here. Again, 1/8 of each of these 8 chloride ions. And the back one's not shown, but 1/8 of each of those gives us a total of 1 atom's worth of material, and half of each of the face-centered ones. That gives us 3 more chloride ions. So how many sodium ions must there be in a unit cell? Well, remember that sodium chloride is a neutral material. All ionic compounds are neutral, and so there must be 4 sodium ions to balance out the charge on the 4 chloride ions. Well, where are they? If we start to look at these are sitting in the gaps in between the chloride ions. And so if we sort of try to locate them, I'll switch colors here. If we sort of try to locate those guys, what we're going to have is here, there's a sodium ion there. And we have to think about what it looks like. It's sitting on an edge. And so how much of that is inside? Well, we have seems like about 1/4 of it is inside, right? If we think about splitting this down the middle, imagining this sodium ion as a sphere, we have a line going down the center, 2 faces coming out at right angles. So looking down on it, it would look something like this with that edge going down through it, 1 face coming out this way, 1 face coming this way, and that's the fraction that's inside this particular unit cell. So we're saying 1/4 each of these things. And so we've got 4 sodium ions across the top face, 4, although they're not all shown, sodium ions across the edges on the bottom face, 4 sodium ions shown here. That's going to give us 4 and 4 and 4 is 12. Times 1/4 gives us only 3. So, well, maybe I was wrong, right? But I wasn't wrong. Where's the 4th one? We want to think about where is the additional space in this thing. And particularly if we try to imagine, and again, I'd encourage you to look at the digital modeling where you can expand a structure and see multiple unit cells coming together. There's going to be a sodium ion tucked in the middle. And so this is a face-centered structure based on the larger ions, the chlorides. But we've got that sodium ion that's going to be stuck in the middle, essentially in the center of this box. So the logic here would say that we have 3 3 sodium ions worth of material based on the edges. That's 1/4 times 12, plus 1 entire ion sitting in the center. That gives us our 4. So as you go down through the calculations here, there's going to be a lot of things where they're asking you to calculate the volume of a unit cell in terms of something, or the radius in terms of something. And this is going to be geometry. So remember back to whenever you took geometry, hit up Khan Academy Geometry if you need a little bit of a refresher. But we're going to focus on a couple of things. We're going to focus on squares as a representation of one face of a cube. And then we're going to think about the cube itself as a 3-dimensional structure. And in many cases, we're going to end up thinking about triangles, particularly right triangles within those structures. So this one for a simple cubic, remember there's no essentially free space, a little bit, but the atoms are packed as close together as possible. We know that the unit cell is a cube with those 8 atoms that we sort of located here. And what we've got is the volume of the unit cell in terms of D0. Well, remember D0 is the edge length. And going up, the edge length is going to be the same. And going back, the edge length is going to be the same because it's a cube, right? So this is essentially saying what's the volume of a cube? Well, the volume of a cube with an edge length of D0 will just be D0 cubed. Parentheses aren't required there, but I wanted it to look clear. All right. So volume of the cell is D0 cubed. So if we can measure the volume, we can calculate the edge length or vice versa. And you'll see some questions in the homework that say, what's the volume of a unit cell if the edge length is blank, or vice versa. What's the radius in terms of D0? Down a little bit further. Well, remember, if we think about that sort of side-by-side structure, and the D0 is this distance from center to center, that's 2 radii, right? I drew that up above. So if we say the D0 is 2 radii, when they use language like this, radius in terms of D0, they want us to calculate radius in terms of something times D0. If we rearrange that first thing that I wrote, you'll see radius is a half of the edge length. Okay? Volume in terms of D0, volume of one atom in terms of D0. Now notice here, what we're trying to calculate is essentially cubic centimeters per atom, right? So the units that we want here are going to be some volume unit per atom. Well, how do we get that? Well, look, we know how many atoms per unit cell we have. We knew that from up above. For a simple cubic, that's 1. And we know the volume of the unit cell, so that would be cubic centimeters per unit cell. And so if we pay attention to our units, this is another opportunity where I get to say, let's pay attention to our units, right? Volume of the atom, we know we're treating this as a sphere, so this is the geometric formula for the volume of a sphere, where r is the radius of a sphere. We can start to calculate this, right? We know that the radius is 1/2 D0. If we take that number, switch colors for you. If we take that number for radius, plug it into this formula right there, you got to do a little bit of algebra. But what we're saying here is 4 pi over 3 times 1/2 D0 cubed. Okay, crunch out the math on that. We're going to end up with centimeters cubed per atom. Okay. So now volume of the atom divided by volume of the cell. Well, we know the volume of the atom because you just figured it out. We know the volume of the cell because you figured it out up here. Divide those two. And what units are we going to get? Volume of the atom divided by volume of the cell. We're going to end up with essentially just a ratio. The units are the same. Volume divided by volume, cubic centimeters on both sides. You're going to get a number. And what this number, the reason there's an equal sign here, in the sort of logic of this thing, they'd like you to have an expression in the first box and then some number over here. And that number is going to be about 0.5. So I'm just going to say approximately equal to 0.5. This is our packing efficiency. So we've calculated here that a simple cubic crystalline structure is about 1/2 filled with matter. The other, roughly 1/2, and you're going to get a more precise number, 3 or 4 decimal places. But the other, approximately 1/2 of this structure is empty. It's literally free space. As you go down, you're going to do the same kind of logic here for a body-centered and a face-centered cubic. I am going to skip body-centered for just a moment and draw face-centered. Because you're going to do the same kind of thing here, but we need to think about what a face-centered structure looks like. So a face of a face-centered structure looks like this. We have that face-centered atom in the middle. We've got the 4 corner atoms pressed as tightly together, but notice that there's a gap between the upper left and upper right, and the lower left and lower right, and so on. There's a gap between those corner atoms. They don't fit tightly together. So although we could label this as our D0 still being here, we can't calculate that directly in terms of radius because they don't touch. There's a gap in there. So it's going to be 2 radii plus some stuff that we don't know, and there's no way to quantify. What we do know is the corner, the face diagonal. And so if we were to imagine going from one corner to the other corner, and I'm going to label that as F, as a face diagonal, that face diagonal is now equivalent or relatable to radii because we have the atoms in intimate contact with each other. They're as close together as possible. And so if we zoom in here, we've got, I'll zoom in for a second, we've got a radius here, another radius, a third radius, and a fourth radius going across that face diagonal. So we know two things. We know that the face diagonal is equal to 4 atomic radii. We also know, because we can consider this as a right triangle, go back to geometry here, a right triangle that has d0 on both sides, the face diagonal is the hypotenuse. So we can do Pythagorean theorem that's going to say d0 squared, one side, plus d0 squared, the other side, is going to equal the hypotenuse squared. Solve that for f. Or we can just say, we remember from geometry maybe that it's going to be the side length times square root 2. That's what it is for an equilateral right triangle. So if we combine these two now, we're going to say that d0 square root 2 equals 4r. That gives us a relationship for a face-centered cubic that is relating edge length and atomic radius. And so you're going to be asked down below to write this in terms of d0 equals so many r's, or the other way around. We can manipulate it back and forth with some careful algebra. The face-centered cubic, or sorry, body-centered cubic, same logic, but now it's a little harder for me to draw. But remember that our unit cell looks like this, and it's got that body-centered critter in the middle. And so now our d0 across the edge length doesn't go through directly touching atoms, nor does our face diagonal go through directly touching atoms. There's going to be a gap in the middle. The one that is solid is the corner to corner. So there's a back upper corner to a front lower corner. That corner to corner or cubic diagonal is the one that's going to have intimate contact. And if we look at that intimate contact going across, what we're going to see is that essentially, see if maybe the diagram up here can help us a little, although I don't like that they show gaps, but essentially we've got the atoms here. If you imagine crunching those up next to each other, we have that 4 radius kind of a setup. And so now the cubic diagonal is 4 radii. What we can think about is one triangle here that's based on edge length. This would be the front or the side face, just like I drew before. Edge length on both sides, face diagonal that we know is equal to d0 square root of 2. Now I want you to imagine a different triangle where I've got here my one, gosh, that got thick, sorry. Face diagonal is one leg of the triangle. d0 is another leg of the triangle, right angle in between those, and the hypotenuse now is my cubic diagonal. So that triangle, if I were to draw it out, right angle, has d0 on one side, the face diagonal, which I already know in relation to d0, and the cubic diagonal. And so I can do the same kind of Pythagorean theorem stuff for this. d0 squared is one side, face squared is the other side, hypotenuse squared. I can plug in the d0 square root of 2 thing there and square it, and what I'm going to end up with is that the length of the cube diagonal, once I crunch out all the math, is actually d0 square root 3. And so when you look in the book, you're going to see several equations kind of just spelled out for you. One of them is this one, that the face diagonal is going to be square root of 2d0, and the cubic diagonal is square root of 3d0. And of course, the edge length is just d0. Those are the geometric things you're going to need to think about as you're going through this. And so it's going to ask you, for instance, a question like this. What's the cube diagonal if d0 is 0.429 nanometers? Well, we have our formula, right? 0.429 nanometers is going to be plugged in for a D0 times square root of 3. You're going to get some number. All right, so they're asking you to go through, calculate density, right? You're not looking up density in a table somewhere. In fact, they give you that number down here. The point is you're supposed to calculate it. Remember that density is mass per volume. So what's the mass of a unit cell? We can calculate that because we know how many atoms are in there, right? For this structure, body-centered cubic, we know how many atoms there are. So we're going to go from number of atoms. We're going to use our calculation to figure out what those atoms weigh. And so we get a mass of the unit cell. We also know the volume of the unit cell. And so if we take mass divided by volume of a unit cell, that's density, right? As long as our mass is in grams and our volume is in cubic centimeters, we'll get a number that we can compare to the literature value 0.97, right? I will tell you that your number is likely to come out just a little bit low, so don't be too surprised, but it should be, reasonably close to 0.97. You're going to do the same kind of logic down below for the face-centered cubic. Right now we're talking about copper atoms here, and you can go through the part B here is very similar. Part C, I want to point out, again, we're determining Avogadro's number, so you may not use Avogadro's number in any of your calculations. So that's a kind of a twist here. You can't use the thing you're trying to figure out. So again, Avogadro's number has atoms per mole, right? Or particles per mole. We're trying to calculate that. And so your number down here at the bottom is going to be a number that should be close to that 6.02 times 10 to the 23rd number that we all know and love. But you can't just write that number down. You're calculating. So notice here, I'm going to calculate along the way how many unit cells there are per mole, right? So there's that unit. And I'm also going to calculate here, oops, sorry, scratch that. That's our answer. I don't know, I can't get my little thing back. Anyway, number of atoms per unit cell up here. All right, so if I'm trying to get atoms per mole, what do I need to do with those two numbers? Well, notice that I can multiply them together. And if I do that, let me try to get my controls back here so I can switch colors. If I do that, my unit cells will cancel. I'm going to end up with units of my answer is going right there, atoms per mole. And again, you know kind of what your target is. It ought to be a large number. Volume of a unit cell here, volume of a unit cell is going to be incredibly small, right? One unit cell is super tiny. So you're going to get a very, very, very small number here. And I would say, that number you should expect in the order of 10 to the minus 20 something. Very, very, very small because we're talking about one unit cell. Molar volume, right? Molar mass divided by density here. Molar mass comes from the periodic table. Just look up copper. They tell us it's copper metal. Density, we can go look up somewhere. Density of most industrial metals is in the 8 to 10 grams per cubic centimeter range. So you can look up copper on your own. You get a number in there somewhere. And again, look at our numbers. Mass here is going to be grams per mole. And if we divide that by density, which is grams per cubic centimeter, grams per mole divided by grams per cubic centimeter, look what's happened to our units. We're going to get cubic centimeters per mole. Right? Now this just says cubic centimeters here because they already told you it's of a mole, but your units are properly cubic centimeters per mole. All right, so this is about using what we know about simple geometry, about the packing of these crystal structures to go through and prove some things, right? To prove the number of atoms per mole here, to prove or calculate the density of sodium metal up here. I would suggest strongly that you pay attention to your units, that you always write units down. Some of your measurements here, you're going to have to change distance units, for instance, from centimeters to nanometers or something like that. You're going to want to make sure you pay attention to those units. And, you know, it makes it a little bit easier sometimes, as I did here. If you write out the units, you can say, oh yeah, I guess I multiply those numbers because that's what the units tell me to do. As you go further down, we've got now here the same kind of a thing with sodium chloride. Remember, this is a face-centered cubic cell, which they tell us here. The larger entities are the chlorides, and the smaller entities are the sodiums, because we know that equivalently comparable sized ions, the positive ion is going to be smaller because it lost some electrons. Remember that our D0 still goes center to center from those structural components, the larger components. And so what does that mean for us? Well, D0 is 2 of the, I guess I should write it this way, 2 of the radius of the chloride ion plus 2 of the radius of the sodium ion. Right, those radii are different, so we can't just say 4 radii anymore. We have to specify plus and minus ions. So that's okay. That's a value that we have. We also know something about our face diagonal, right? That's going to be just going through chloride ions. And so we can go through and start doing some math here. So think about those kinds of relationships and what we know from up above. They say here the cations are in the octahedral holes. Again, look at the digital model, but an octahedral hole is that space in between ions of this size. The lab talks a bit, pardon the scrolling here, so maybe I can just jump up to the page. The lab talks a bit up in the reading about, no, I guess I can't. Where is it? Sorry, I didn't mean to scroll this much. I just can't find the table that I'm looking for. Because it was further down. When you look at this radius ratio rule here, they're going to ask you what the predicted structure is. And so essentially what you're doing is you're going to look up the data for the radius of each of these ions, potassium and iodide, copper and bromide, so on. And if I can find that, it's really embarrassing that there it is, great. So here's the table. Sodium and chloride, if you look at their radii, you're going to see that they fall into this range. That's why they said the cations fall into octahedral holes. It's just the size of the hole based on the structure. When we look at the other ones, you're going to determine if potassium iodide and copper bromide, whatever, fall into these other structures. Okay, so cubic holes, octahedral holes, using the radii that are given to you in the table that I cannot find for the life of me, and I'm going to quit scrolling so that I don't make you dizzy, or dizzier. So at any rate, that is kind of the idea of the crystal structure lab. I would strongly, strongly encourage you to go and look at that digital modeling software that I have for you, because it is much, much easier to see this and be able to turn it and manipulate it and add layers and break it apart into unit cells. So work through this. Be careful with your algebra. Be careful with your units. When you're all done with this lab, you can take photographs or scans of what you've done and upload that, and that'll be your assignment for this particular lab activity. So with that, I'll say good luck. Let me know if you need anything, and keep up the good work.